Assalamu alaikum students. Today our topic is electromagnetism and subtopic is force on a current carrying conductor in a magnetic field. We are going to do the SLOs. Describe that a force acts on a current carrying conductor placed in a magnetic field. Second SLO is describe that a current carrying coil in the magnetic field experiences a torque with the help of Fleming's left hand rule. Force on a current carrying conductor in a magnetic field. We know that a current carrying wire has a magnetic field around it. We have done this topic in the previous lesson. If we place this wire in another magnetic field, the two magnetic fields may interact and may then produce a force on the wire. That means if the wire which has current and has its own magnetic field placed in another magnetic field in between the poles of a magnet, then both the fields interact to each other and may produce a force on the wire. This effect is sometimes called the motor effect. You see in that figure, there is a wire, okay? The current in the wire is into the paper or into the page, and there is a magnetic field from north to south. Magnetic line of force is from north to south. Field due to permanent magnet. These are the lines of field due to permanent magnet. Field due to current carrying conductor. If the current is goes into the paper, then according to the right hand grip rule, the direction of current is clockwise. This is the direction of the clockwise. Okay, so both are the magnetic fields. All right, after the interaction of the both magnetic fields, this thing happens. Combined field causing force on conductor. This force of the magnet, permanent magnet from north to south, and the other force of this current carrying conductor, which is into the page. Because of this force, the wire force out of the field. Okay, you see the wires force out of the field. Both the magnetic field interact to each other and conductor force out of the field. Force on a current carrying conductor in a magnetic field. A wire is hung between the poles of horseshoe magnet. When the circuit is closed, that means current is flowing. We observe that the wire is thrown outward. That means a force is exerted on the wire and the wire is moved outward side. If the current is reversed, the wire swings in the opposite direction, that is inwards or inside. If the magnetic field is reversed, the wire swing outwards again. You see the diagram. Okay, this is a wire hung in a horseshoe magnet. The direction of the horseshoe magnet is from north to south. You see, from north to south, north is written. Okay, the magnetic field from north to south, this, and the current is from positive to negative, from this side to this side. Current is going in this direction and then come back to negative. All right, so direction of current is this and the direction of the magnetic field is upward. All right, so what would be happen? This wire which is hung inside the magnetic field is move outwards and move upward, because when the current is flowing through this wire also has its own magnetic field, and there is magnetic field of this permanent horseshoe magnet. So both the magnetic field interacts each other, and because of this the wire is pushed out or pushed in. It depends on the direction of the current. From this we can deduce that current carrying wire experiences a force when placed in a magnetic field. This force acts perpendicular to both the direction of the current and the direction of the magnetic field. That means direction of the current, direction of the magnetic field and direction of the force is perpendicular, mutually perpendicular to each other. Factors that affect of the force on a current carrying conductor in a magnetic field. These are the factors that depends on the force on a current carrying conductor. Number one, strength of the magnetic field. If we are using powerful magnet, then the force is greater. If we are using the weak magnet, the force is the weaker. Second factor is size of the current in the conductor. Size of the current in the conductor means amount of current. If we are supply more the current, then the force in this wire or conductor is greater. If we are using low voltage supply, then the force is weaker. Third factor is length of the conductor in the magnetic field. This length of the conductor in the magnetic field. If the length is greater, the force is increased. If the length is smaller, the force is decreased. And fourth factor is direction of the conductor relative to the magnetic field. As I told you earlier, these are perpendicular to each other. If the conductor is placed parallel to the magnetic field, so there is no force or there is zero force. So direction of the conductor relative to the magnetic field is also important. It is perpendicular to each other or makes 90-degree and to each other. To determine the direction of force. How can we determine the direction of force? We know that the force is acted on a current carrying conductor when placed in a magnetic field. But what is the direction of this force? Right side or the left side or clockwise direction or anti-clockwise direction? To find this direction of force, we use Fleming's left hand rule. According to the Fleming left hand rule, stretch the thumb, forefinger, and the middle finger of the left hand mutually perpendicular to each other. If the forefinger points in the direction of the magnetic field, the middle finger in the direction of the current, then the thumb would indicate the direction of the force acting on the conductor. According to this figure, if you placed thumb, forefinger and middle finger, this is the thumb, okay, it indicates the direction of force. This is the forefinger, it indicates the direction of the current, and this indicates the direction of the magnetic field from north to south, and the middle finger indicates the direction of current in the wire. So you see all three fingers are mutually perpendicular to each other. 90-degree over here, 90-degree over here and 90-degree over here. So this is called Fleming's left hand rule. Fleming is the name of the scientist. To dedicate the scientist, we know that Fleming's left hand rule. Okay, these are the diagrams to show the clear picture of this Fleming's left hand rule. You see, this is horseshoe magnet and this is a current carrying wire placed in this magnetic field. The direction of current is downward. So the force acting on this wire is upward, outside the magnetic field. If you check this with the help of this, you can easily understand the force on the current carrying conductor placed in a magnetic field. You see another the picture, the direction of the current is downward. This the middle finger shows this direction of the current like this, and the direction of the magnetic field is now north to south, north to south. And then the force acts on this wire upward. That means wires move upwards. I hope you can easily understand the force on a current carrying conductor placed in a wire, the direction with the help of Fleming rule very well. Thank you, girls and boys.